right, let's go. Okay, so what we saw last time was the method of separation, right? So that's where we had equations of the form y prime is equal to f of x g of y, where I could separate variables because things factored. Now, generally, this is not going to be a method that is going to be universal because the fact that the function on the right-hand side can be factored into a piece only in x and a piece only in y is pretty hard. So the method that we're going to talk about today arises from the following sets of observations. So I'm going to write down some reminders from ancient history. What is the derivative of x squared e to the x? How do you compute that? What's the rule? Product rule. Okay, what is it?
2x e to the x.
2x e to the x plus x squared e to the x. More generally, dy dx of fg is f prime g plus fg prime, right? That would be the way you learned that originally, probably. So I can make this slightly more sophisticated by writing down something like d by dx of x squared y. So now I want you to think here implicitly that y is a function of x. So compute that using implicit derivatives. What should that derivative be? 2xy.
Plus x squared y prime.
2xy plus x squared y prime, or dy dx, right? So symbolically, if I have y implicitly as a function of x, I can still compute product rules. Okay. So if I recognize that something is the result of a product rule, I can pull it back to an expression involving a derivative. So what I mean by that is, if I wrote down something like cosine of x y prime plus sine of x y, and I ask, is that the result of, I mean, it kind of looks like it should come from a product rule. There's a y and a y prime. So if I'm following this rule, this could be the function, I don't know, f, and this would be f prime. And if this also has the relationship that g and g prime have this relationship, so that this function's, I have this backwards, g, I do this right, hold on, I gotta put this this way. There, I fixed it. Okay, I wanted it this way. So if I look at this and I say, okay, y's derivative is y prime, and sine x's derivative is the cosine of x, that looks like it resulted from taking the product rule of something, right? The derivative of a product of functions. And so if I recognize that something is the derivative of a product, I could just have written this as, oh, I recognize that this is d by dx of the sine of x times y. If I took the derivative of this, that's what the result would be, right? So sort of a key tool that we're going to be working with here in 1.6 is this observation that if something was the result of a product rule, I could undo it. So I'm going to set up an easy differential equation now. So suppose I give you the following differential equation. The point of the differential equation is I say solve for y, which means I want to know the function y that solves the differential equation. And I write down the cosine of x times y plus the sine of x times y prime is equal to 1. Now, with the techniques that we've built up so far, your first thought here might be, just like when you learn to integrate, you always check to see if u substitution works first. Your first thought might be, maybe it's a separable differential equation. Well, is it separable? And the answer is, well, I would have y prime is equal to 1 minus the cosine of x times y, all divided by the sine of x. I don't see a way where I'm going to be able to factor this as a function of y times a function of x, because there's this 1 up here that breaks the fact that the idea I could factor this. It's not separable. No. So the next thing I might think is, well, maybe I'm going to get lucky, and that will be the result of a product rule. Oh, look, we already noted it is, right? So because the expression on the left-hand side is the result of a product rule, I could just immediately observe that I could rewrite this equation as d by dx of the sine of x times y is equal to 1. Notice when I did that, I've reduced the number of y's in the equation to just one of them. And the derivatives are gone too. There's no y prime anymore. There's just y. And now, if only I could get rid of the d by dx, then I could solve for y. Fortunately, when we built this mathematics, we built an operation that undoes derivatives, which is integrals, right? So the fundamental theorem of calculus says that the integral of a derivative is equal to the original function. So if you integrated this expression on both sides, the integral of d by dx of the sine of x times y dx is equal to the integral of 1 dx, there's not any work to do on this side. You're just integrating a derivative. And the result of doing that is just the sine of x times y. On the right-hand side, I have some work to do because I have to integrate 1. And if I want to finish the problem by solving for y, I can divide through by sine to get y is equal to x over the sine of x plus c over the sine of x. That's it. If a differential equation had the property that I can rewrite the left-hand side as a product rule, I can always do this. I can rearrange the left-hand side to extract the d by dx, and then I can just integrate it away. The problem is, of course, not every equation is written that way. So here's example 2. What if instead I gave you the differential equation y plus the tangent of x y prime is equal to the secant of x? Now I look at that and I think, well, I'm doomed. It's not separable because I'm never going to be able to factor the right-hand side because there's going to be an addition over there. And yeah, okay, the derivative of this function is y prime, but the derivative of tangent is not 1. So it's not a product rule. Shoot. If only there was some way I could modify the equation so that it turned into a product rule. So notice that the way I got this equation was I just took the previous one and I divided everything by the cosine. So this equation is that equation, but everything divided by cosine. I've hidden an equation that looks like a product rule by dividing it by something. So how could I undo that? So if I took the entire equation and magically somehow it occurred to me, if I multiplied everything in that equation by the cosine of x, for some reason, I decided to do that, the result would be the cosine of x times y plus, tangent times cosine is sine. Sine of x times y prime is cosine of x times the secant of x is 1. Oh, look, I've made it back into the original equation again. So now I've taken an equation that was not the result of using a product rule, and I've turned it into something where now it is. So from this point, I could continue solving this equation the same way I solved that one. I could say, oh, that means I could write this as d by dx of the sine of xy is equal to 1. Oh, so yeah, that's right. Right? So the question you should have is, what if I didn't just take an equation that I already knew the solution to, and I just wrote down, I divided it by something to trick you and wrote it into a new form? Like, could you have come up with the idea that we need to multiply by cosine on your own? Is there a way you could have cooked up that magic function? So before I give you the answer to that, which of course is yes, or we wouldn't be talking about this section of the textbook, I'm going to give you one more example to look at. And then I'm going to start writing down some terminology, and then I'll tell you the answer. So the second equation that we're going to look at is also an example in the book, which is a pretty nice one. So let's look at this guy. Example 2. Y prime plus 1 over xy is equal to e to the x. And let's say that x is positive here so that I make sure I don't accidentally divide by 0. The first question you should ask yourself after you observe that this is not separable is the left-hand side the result of a product rule? Dang. Okay, y turns into y prime, but the derivative of 1 is certainly not 1 over x. Shucks. I guess I'm finished with the problem. Can you think of something like, is there an easy way that I could multiply all this by something to get something that looked like a product rule? Now this one, don't use a formula here. There's a very simple fix for this one.
You multiply by x.
So what if you did? If you multiply this by x, then you're going to get out the expression xy prime plus 1y is equal to x e to the x. And now that is the result of a product formula because x prime is 1 and y prime is y prime. This is now a product rule. And the thing that we multiplied by, this x right here, this is what we mean when we call an integrating factor. It's an auxiliary function that we it's kind of like we're uncanceling a 1 in a really magical way. We're making the equation more complicated, but in a special way that turns this into a result that we want, which is a product rule. From this point, if I wanted to now, since I've observed, hey, multiplying by this thing, x, has turned this into the derivative of xy, I don't need to do anything fancy here. I don't need to, the whole point of multiplying the x in was that this got pulled back into the derivative of a product. How do I get rid of it? Integrate. Now, this is where I'm going to sort of really try to convince you not to go wrong when you're doing this. The wrong way to approach the left-hand side of this would be to say, okay, I'll take the derivative of xy, and then I will use integration by parts to put it back together again into the answer. What this is asking you to do is to integrate the derivative of xy. What is the answer? xy. Derivatives and integrals cancel. xy is equal to the integral of x e to the x dx. So the point is, the left-hand side of this, I did no work. I identified the right function, or you identified the right function, rather. We observed that after having done that, this looks like the result of a product rule. We wrote it as a product rule, and then we just canceled the integral by integrating both sides, or the derivative by integrating both sides. And now, all you have to do is remember how to integrate x e to the x. So, I'm going to point out, everything we do in this chapter, because the method here is going to involve multiplying by functions, almost every integral in this is going to be a product of functions on the right-hand side, which means you should expect that you're going to be working with u substitution, integration by parts, and partial fractions are going to be common methods that you need to handle the exercises in this section. So there are going to be techniques here that maybe you haven't thought about in a long time. I'm going to finish this one up just to remind you of, if you haven't seen it before and you want to learn it, there's a fast method for doing integration by parts on something like x e to the x dx. Some people learn it this way. So there's a differentiation column and an integration column. The thing that you want to cancel, you put in the differentiation column and take derivatives until it disappears. The thing you want to integrate, you integrate until you have an equal number of terms there to get you down to the 0 step. You multiply across, and then the sign that you stick on front alternates. This is essentially just uv minus v du, but in a short algorithmic form. So the answer to this equation is x times e to the x minus e to the x plus c. So this is a quick algorithmic way of doing the old integral of v du is equal to uv minus the integral of, udv is uv minus the integral of v du. So if you've not seen this before and you'd like to learn it, come ask me in office hours. It's way faster than doing let u be this and let dv be that and do your sort of chart way. The other thing I'm going to let you do explicitly in this class is If you can just eyeball the solution to an antiderivative problem, you are welcome to do so. Just don't get it wrong. Okay, so what that would say in the case that we're working on is xy is equal to x e to the x plus minus e to the x plus c, and that means that y is equal to e to the x minus 1 over x e to the x plus c divided by x. And there is a point to be made here about, when are you allowed to combine things into the arbitrary constant and when you're not allowed to. X is not a constant, so it doesn't interact with arbitrary constants by being absorbed into them. A better way to think about this is, in the original differential equation, there is behavior that is intrinsic to the system that does not depend on any initial value that you give me. There's no plus c's in this part of the equation. Those are always part of the answer, no matter what the initial value of the equation is. Y of 0 is anything you want, that is always there. The only part that changes is this part. So, in a lot of cases, we think of this as intrinsic behavior in the system that's dictated by the differential equation itself, and this is just a consequence of the initial condition. So you can think of intrinsic versus extrinsic, or no external force, and then the piece that's added by external force. All right, so let's write down the actual method. So this is going to take some terminology, and now I'll get to prove something. Okay, so a linear first order differential equation. If you want to think about what these things model, remember population growth, simple mixing problems are the consequence, or what we can model with these things, is of the form a of x y prime plus b of x y is equal to c of x. Every first order linear differential equation looks like that. And this is where our functions a of x, b of x, and c of x are defined on some interval. So no asymptotes allowed. If a of x is not equal to 0, so there's no point at which a of x is equal to 0, then I'm allowed to divide by it, right? If something's not 0, I can divide it away. So if you took the initial equation and you divided everything by a of x, you can write y prime plus p of x y is equal to q of x. So if I divide everything by a, there'll be a 1 in front of the y prime term. And this is called standard form. So essentially the idea with first order linear differential equations is I almost always want to think about them in this form. In later classes and in your applications that you go into in your major courses, you'll learn how to deal with cases where a of x is equal to 0. In fact, if you continue on to 344, I'll teach you how to deal with those. Or I will, or somebody will, maybe not me. All right, so here's the theorem. Notice the standard form of this looks an awful lot like it's going to be the result of a product rule, because there's a y and a y prime, and there's a p of x, but for some reason there's no the thing that would spit out a p of x. So this is set up to be modified by a multiplicative function that will turn this into the result of a product rule. So here's our theorem. This is the integrating factor theorem. If y prime plus p of xy is equal to q of x, then I of x is equal to e to the integral of p of x dx is an integrating factor. And the derivative of I of x y is equal to I of x times y prime plus p of xy. So essentially, the x that we pulled out, or the sine x we pulled out in the earlier problems, this is the formula where that comes from. So this is a formula for telling you the thing that you're going to multiply both sides of the equation by. So I'm going to prove that that formula works, and then we're going to do a bunch of examples of actually calculating these things and solving the equations. Okay, so again, to emphasize, this thing, the whole point of the integrating factor is to turn the differential equation into a product rule. And this step right here is so important that I call this the key idea, in capital letters in the notes even. This is the work-saving step. All right, so let's write down an example. Or sorry, the proof first, I suppose. So let's actually calculate the derivative. So let's let, this is a proof, we'll let I of x be equal to e to the integral of p of x dx. What is I prime of x? The derivative of e to the anything is e to the anything
Times the derivative.
times the derivative of the anything. So e to the anything times the derivative of the integral of p of x. What's the derivative of the integral? It's just p, right? Derivatives and integrals cancel. The derivative of the integral of p of x is just p of x. So we'll store that off to the side for a second. Now, what I'd like to show is that this line is true. The derivative of the product of I of x with y is equal to I of x times that stuff. The derivative of I of xy is equal to y prime times I of x plus y times d by dx of I of x. So that's y prime times e to the integral of p of x dx plus y times e to the integral of p of x dx times p of x. But then can I just factor the e to the integral of p of x out of both parts? E to the integral, it's like, this is like a cheesy trick. Y prime plus y times p of x. I do this backwards. Let's see, y prime times I. Yeah, that's right. I got my p in the right spot. Here we go. And I think that's just I of x again. Now, if this seems like, to you like, well, of course this is what it did. You set it up that way on purpose. Well, yeah, exactly, right? We built this precisely so that it would have this effect. So the idea is, as soon as I calculate an integrating factor, the instant I have it, I can multiply an equation that shows up on the left-hand side of a differential equation by this with I of x, and then just immediately skip all this crap and write that down. There's no extra work to do. Once I've identified the integrating factor, I can just immediately write down that it was a product rule. So how does that work in practice? Do not do more work on these problems than you have to. So let's look at, let's see, a good example here would be something like this one. Example, dy dx plus xy is equal to x e to the x squared over 2. So I'm going to look at that and think, all right, well, it's in the right form. It's definitely of the form y prime plus p of xy is equal to q of x. So I've got a coefficient of 1 out front. P of x is equal to x. And so I of x is equal to e to the integral of x dx. Now I don't need every integrating factor. I just need one of them. So when I integrate x there, I don't actually have to put a multiplicative or a constant. I can just find a single integrating factor. Integral of x is, okay, so this is x squared over 2. So there is my integrating factor right there. E to the x squared over 2. What does this say? So the whole point of integrating factors is once I've got the integrating factor, I want to create the product rule. So I'm going to take my original equation and I'm going to multiply both sides by the integrating factor. E to the x squared over 2, that's my integrating factor, times y prime plus xy is equal to e to the x squared over 2 times x e to the x squared over 2. Now, I'm not gonna write any additional work down except to say, oh, I want to immediately apply the key idea here. The whole point of creating the integrating factor was I know the left-hand side is going to pull back to a product rule now. And I know exactly what it's going to pull back to. Okay, so my lecture got cut off because the camera died mid-recording. So let me finish this example and I'll do one more. So where I left off in my discussion was that the whole point of multiplying through by an integrating factor is that we are setting up an equation so I can use that key idea step. And remember that the key idea step said that if I have I of x times y prime plus y times p of x, that I can instantly write that with no technique and no work as the derivative of I of x times y. So I don't need any technique, I can just do that. So in this particular example, we're going to take the left-hand side, apply the key idea to it, and we're going to get that this is the derivative of e to the x squared over 2, which was our integrating factor, times y. And on the right-hand side, we'll multiply these things together to get x, e to the x squared. And the power of this method is that I don't actually have to do anything to this d by dx to integrate it away. The integral of a derivative, they just cancel each other. And what's left behind is the e to the x squared over 2 times y. You might wonder where the plus c goes. We're going to pick up an arbitrary constant on the right-hand side once we do the integration step. So if I integrate both sides, the integral of the derivative of e to the x squared over 2y dx is equal to the integral of x e to the x squared dx. On the left-hand side, these just cancel. The integral of a derivative is sort of doing something and then immediately undoing it. So we're looking at e to the x squared over 2y. And on the right-hand side, we can observe that I could use u substitution here. If I can just eyeball the antiderivative, I can just write it down. You could use u sub here with u is equal to x squared. If you do that, I think what you should find is that you get 1/2 of e to the x squared plus c. It's your answer one way or another. And then to finish the problem, if you divide through by e to the x squared over 2, that will get you your sort of final form for the solution. Y is equal to 1/2 of e to the x squared over 2 plus c times e to the minus x squared over 2. And one thing I pointed out about the structure of the solution and why sometimes it's nice to have explicit forms is that we have a piece here that doesn't depend at all on the initial condition that we chose for the problem, and a piece that does. That's what the arbitrary constant does. But further, as time goes on, e to the minus x squared over 2 goes to 0 as x goes to infinity. And what that means is this term will disappear in the long run. And in physical applications, these are called transient terms. So they count at the beginning, but they sort of disappear as time goes on. Okay, so let's do another example. The second example I did in class. And that was an example where the function was not quite in the right form. We had to recognize it's not in the right form and then put it in the correct form. And that example was this. We had x, y prime, minus 2y is equal to 2x squared natural log of x. So make sure it was x squared, just regular old x here. Yeah. Okay. So this is linear, but it's not in the correct form because I have a non-one coefficient for the y prime term. So what we're looking at here is something that looks an awful lot like an a of x y prime plus a b of x y is equal to a c of x. In the statement of this problem, we were told that x has to be positive, and that's good because it means a of x is never equal to 0, and so I can divide everything by a of x to put this thing in standard form. So if I divide through by 1 over x, or multiply through by 1 over x, that's going to get me standard form. Y prime minus 2 over xy is equal to 2x times the natural log of x. Now we are in the correct form because we're looking at something in the form y prime plus p of x, y is equal to q of x. I have to be a little bit careful here to keep track of the sign because the form we're looking for is y prime plus p of xy is equal to q of x. So there's a plus sign here. Since we have a negative here, that means in our case p of x is equal to minus 2 over x. That puts me in position to calculate my integrating factor. So I of x is e to the integral of p of x dx, which is e to the integral of minus 2 over x dx, which is e to the minus 2 times the natural log of x. I am not putting the absolute value signs in here because we know that x is positive and the absolute value of x is just equal to x when x is positive. I can't just immediately cancel the e and the log because the negative 2 is interposed, but I can rewrite this as e to the natural log of x to the minus 2, which is just x to the minus 2. So there's my integrating factors, 1 over x squared. So the whole point of integrating factors is once I know what it is, I can just multiply the correct equation by that integrating factor. In this case, this is the form of the equation that I want to work with because that was the standard form equation. So I'm going to write down x to the minus 2 times y prime minus 2 over xy is equal to x to the minus 2 times 2x natural log of x. The key idea step applies here. So I don't have any more calculus to do because the key idea points out that once I've multiplied the right-hand side of a first-order linear differential equation by the integrating factor, I just know that I've made that into a product rule form. So I can write that as d by dx of the integrating factor times y. That's why we did that. And on the other side of the equation, we're going to get a 2 times a natural log of x over x. Integrating both sides, so we're going to integrate the derivative, which just cancels it. That gets me x to the minus 2y is equal to the integral of 2 times the natural log of x over x dx. You can do this with a u substitution where u is equal to the natural log of x. If you're crazy, you can try to do it with integration by parts, and you get the same answer. In either case, you're going to end up with x to the minus 2y is equal to the natural log of x squared plus c. And so finally, y is equal to x squared times the natural log of x squared plus c times x squared. And if I give you an initial condition, you can solve for c just by plugging it in. Okay, so those are the remaining 2 examples that I did in lecture. One thing I pointed out about this is that it's typical that we get complicated expressions to integrate over here because we're always going to be setting up a product of functions on the right-hand side of these equations because we're multiplying by an integrating factor. And so what that means is that we're going to have to remember how to use techniques that involve integrating products of functions. So your basic set of techniques there are u substitutions, integration by parts, and occasionally something like partial fractions. Okay, so sorry about the glued together nature of these videos.